Welcome back everyone to another Applied Calculus lecture. Today's content is going to have us jump forward a little bit into section 6.1. In chapter 5 we introduced the notion of a definite integral, and we sort of skirted around the question of how we can find and solve a definite integral. We sort of spent most of our time talking about what they mean, what the interpretations are. Chapter 6 here is going to begin the conversation of how to find a definite integral. To begin with, however, we need to introduce some standard notation and vocabulary to make sure that we're all on the same page. So to begin with, we're going to introduce the following notion. We're going to say that if you have a given function, say capital F, and you know that its derivative is given as, say, little f, that is, of course, this equation holds true, we're going to say that since capital F, or we'll say since capital F is sort of the function that occurs before little f in terms of differentiation, we're going to declare capital F to be now what's called the antiderivative of little f. So in some sense, capital F is what exists before we differentiate it and get little f. So for example, if we had a function like x squared, and we find the derivative of x squared, we get 2x. And so what we're going to then say is that this before function, x squared, is going to be now what we're going to call the antiderivative of 2x. Because again, it's what exists before you differentiate it and find the derivative. Now there is a small caveat. I use the word "and" here. This is important because there are many antiderivatives. For example, here I could have chosen x squared like I did up here, but if I would have chosen, say, x squared plus 3, this would have been a perfectly other valid antiderivative, because when I differentiate the 3 here, the 3 goes away because derivatives kill constants. So x squared plus 3 and x squared both could have been completely valid antiderivatives. Antiderivatives are not unique objects, and so usually we'll need some additional information if we do want to narrow down our choice of antiderivative to a very specific function. So what we'd like to be able to do right now is we would like to begin trying to investigate the values of an antiderivative. And in order to do that, what we're going to do is we're going to import some, well, basically we're going to go back to what we've already talked about and sort of mathematize it a little further. So the first thing that we need to import here is the following. What we've learned so far is that the definite integral of a function turned out to give the area under a curve, where we learned that this is signed area, not necessarily just straight up area. We also learned that when the function in question was a rate of change, then the definite integral was giving total change of the quantity. Mathematically, what this would mean is that if we're given a function f of t and it's a rate of change of a given quantity, then what we determined was that the definite integral from a to b of f of t dt was actually determining area under the curve, meaning the total change in quantity between a and b. And we approximated this using rectangles. However, we sort of kept using this language because it sort of relates to our intuitive notion of rates of change and velocity and stuff like that. But at its core, as soon as we use the phrase rate of change, what we're really saying is that the function f of t is the derivative of something. Because that's the point of the derivative, is it's the rate of change of something. So if this function f of t is the derivative of something, that means it's the derivative of one of its antiderivatives. So what that means is capital F is now going to represent the actual quantity that's being referenced. So when we say the total change in quantity, what we mean is the total change of f from a to b, which is of course going to be f of b minus f of a. And so what we're going to do now is we're going to take this statement and interpret it in terms of antiderivatives, and that'll give us one of the most important theorems in all of calculus, and it's earned its name, the Fundamental Theorem of Calculus. Explicitly what it says is that if f of t is a continuous function on some interval from a to b, and f of t is n antiderivative, then the total change, the definite integral from a to b of little f, is equal to nothing different than its antiderivative f evaluated at b minus its evaluated at a. This is a super compact formula that really has a lot of power to it. One way to think of the power here is that this object on the left required us to interpret a geometric area. So this had us approximating with rectangles and stuff like that. Whereas this object on the right, all we have to do is find an antiderivative. So if we can somehow do a good job at starting with 2x and figuring out whether we want x squared or x squared plus 3, if we can undo the derivative in any reasonable way, then it turns out that this geometric rectangle nonsense is nothing more than finding an antiderivative and then performing this difference evaluation. And that's somewhat powerful, and we can definitely use this to great effect. That's just one example of why this theorem is so powerful. We could spend an entire lecture on it, but what we're going to do for now is just state this and see what we can do in the immediate future. So now we can start asking a question. The new question we want to try to ask is, okay, we need to figure out how to find antiderivatives. That's going to be the first question we want to try to answer. But while we're at it, we're going to also try to ask ourselves how they look. We know, for example, that there's an intimate relationship between a function and its derivative in their graphs, right? We spend a lot of time talking about curve sketching. But for antiderivatives, we're kind of going in the reverse way. Instead of computing a derivative, we're undoing a derivative. So in theory, there should exist also some intertwining of their graphs, a function and its antiderivative. For starters, let's take a look at a problem and see if we can't start to sniff out how we find antiderivatives. So this example says, here's a derivative. F prime of t is 1.8 times to the power of t. They also gave us some additional information, which is going to be useful. While we're at it, just so we're clear so you understand what I'm saying half the time, this additional piece of information is going to be referred to as an initial condition. So when I use that phrase, you know what I'm referencing. Our objective is to posit a potential antiderivative for this function, and then once we find that, we want to evaluate it at 1. So for starters, the way we're going to approach this is we're going to remember all of our derivative rules, and we're going to do our best to try to figure out what could I have taken the derivative of to get this exponential. Well, you think for a quick second, and maybe we'll actually write down that question just so that we're clear. The question here is, what could f be? Well, let's remember what exponentials do when you differentiate them. So what we're going to do is we're going to recall that if I took the derivative of, say, 1.8 to the x, what would I get? I would get the natural log of the base times the function itself. Okay, well that's not good enough, right? We found something that if I differentiate it, I get the exponential, but then I have this dumb constant sitting out front, which is not quite what I'm looking for. But I'm pretty close. Remember that derivatives actually don't change with a constant. So if I would have, for example, divided this right side's ln of 1.8 to the left-hand side, I would have generated a function whose derivative would turn out to just be 1.8 to the x. So that's an observation we can make. Instead, if I would have differentiated like 1 over the natural log of 1.8 times 1.8 to the x. This would have just given me 1.8 to the x. Bingo, that's what I want. That's a good thing. I found a function whose derivative is exactly what I'm looking for. But remember that when I take the derivative of something, all of its constants will always get crushed. So I don't know right now that this is exactly the function f I'm looking for. It could be this plus 2, this plus 5, this minus 1,000,000. I don't know. So what that means is, really what we've determined is that the function f of t looks like 1 over the natural log of 1.8 times 1.8 to the t plus c. We call this magic c for some constant c. Our objective is to figure out, if possible, what is that c? And we have to ask ourselves whether we have sufficient additional information in the problem in order to determine what that c value is going to be. Fortunately, the answer to this is yes, as it comes in the form of an initial condition. So, what we'll say here is that since f of 0 is equal to 2, this is equivalent to, well, this is my proposed f. So I'm going to plug in 0 there. I'm going to get 1 over the natural log of 1.8 times 1.8 to the 0 plus magic c is going to be equal to 2. But of course, anything to the 0th power is a 1. So this is going to turn into 1 over the natural log of 1.8. So we're going to get 1 over the natural log of 1.8, but then I'll take that and move that to the other side. And what I'll end up with here is I'll get c is equal to 2 minus 1 over the natural log of 1.8. And that's going to be some number. I don't know what that's going to be, but that's going to be the c value. So if we want to answer the actual question, which is what is f of 1, we'll write that therefore f of 1 is equal to, we're going to take this equation, plug in a 1, so we're going to get 1 over 1 ln of 1.8 times 1.8 to the 1 plus c, which we know is 2 minus 1 over the natural log of 1.8. And that's going to be our f of 1. And we could try to clean this up somewhat if we really wanted to. Right, you could combine this. You could rewrite this as something like 2 plus, and you could get a common denominator, 1.8 minus 1 over the natural log of 1.8 if you wanted to. But essentially, that's going to answer the question. So the point of this example is to illustrate how we might come up with antiderivatives. Really, what we see is that it boils down to asking some questions, remembering some differentiation rules, and kind of making an educated guess as to what the final derivative would be. Once you do that, you have to remember that antiderivatives are not necessarily unique, so you'll always pick up this magic constant c until an initial condition can tell you what that c value is, and only then can you determine the unique antiderivative for which you can then evaluate at the desired point. So this answers a question, at least somewhat, in the direction of how do we find antiderivatives? What we now want to try to answer is, how do they look? To answer how do they look, we're going to remember some information we imported a long time ago. Remember the following fact we learned in section 2.2 when we introduced the derivative. We said that if you have a function and its derivative is given as f prime, we determined that if f prime was positive, the function f was increasing. Similarly, if f prime is negative, then the function is decreasing. And if our f prime was equal to 0, then f is constant on that interval. We use this information to also deduce something about concavity by simply swapping out f and f prime with f prime and f double prime. So if we can apply the same set of rules to a function, its derivative, or its first and second derivative, we can work the other direction, and we can do the same thing with a function and its antiderivative. So using the same notation we've used so far in the lecture, we're going to let capital F be an antiderivative for little f, so that its derivative is f. And then what we're going to do is we're going to do a proper replacement. What we'll find is that if f is an antiderivative, if capital F is an antiderivative of little f, then instead of the derivative, we're going to say, if little f was positive on an interval, then its antiderivative, capital F, is increasing. And if little f is negative on an interval, then capital F, its antiderivative, is decreasing. And if little f is 0, then its antiderivative is constant. This knowledge allows us to be able to start sewing together some graphs of what a function's antiderivative might look like. Additionally, we'll find that accuracy of our graph is going to be greatly aided by this fundamental theorem of calculus, because the fundamental theorem of calculus allows us to evaluate an antiderivative at some points and relate that to the area under the curve of the original function. So if we can approximate and compute areas of our function, we can get some accuracy for what the coordinate values are of the antiderivative capital F. So let's take a look at an example. For this example, we're going to consider a graph of a function's derivative, f prime. So follow along as I fill in the blank here of what this graph is supposed to look like. It's going to be a graph living entirely in the first quadrant with an x-axis tick mark interval of 6. So that's 1, 2, 3, 4, 5, and 6, where so maybe I should have moved this axis up a smidge. So let's move it up real quick. There we go. Put the vertical axis there. And so what we're going to end up having is we're going to have the function cross the x-axis at 2 and 5. And it's going to look maybe something like this. In particular, we're going to be given some amount of information about the area under its curve. The area of the first bump here is going to be known. The area underneath the curve down here is also going to be known. And the area above the curve to the right is also going to be known. In particular, the first area is going to be known to be 14. The area down here is 20. So what that means, remind you, since it's beneath the axis, the area is 20, so that's going to be unsigned area. But in particular, if I were to, since this function itself is the function f prime, if I were to integrate this f prime from 2 to 5, I get signed area and I'd get negative 20. Okay, that's a very important observation. You pick up the negative when you do the derivative. When you do the definite integral. And then we're also going to take as assumed that the area for this rightmost region is going to be 12. So if all we know is, if all we're given is an initial condition of f of 0 is equal to 10, so let's remind ourselves, highlight that so we don't forget about that. Our objective is to sketch a graph of f. If this is a graph of its derivative, can we give a graph of f? While we're at it, maybe we can come up with coordinates for the local max and local mins. So first of all, we're going to want to use these sort of rules. So if a function f is positive or negative at an interval, that tells us that its antiderivative is increasing or decreasing. So let's write down some of our quick observations here. So we'll say this. By the picture, we see that f prime of x is positive for what? Regions 1 and 3. for x being greater than 0 and less than 2, and x being greater than 5 and less than 6. And we found that f prime of x is negative for the middle region, which is going to be x between 2 and 5. So if this is where the derivative is positive or negative, our rules indicate that the first bit tells us that the antiderivative f is going to be increasing, and the second bit down here tells us that the antiderivative f is decreasing. This is important because what we've determined now is that our function f, the antiderivative, is increasing and then switches to decreasing and then switches back to increasing. This, of course, defines the existence of a local max and a local min. So right off the bat, just by interpreting this information, we're concluding here that x equals 2 is a local min or max. We're going from increasing to decreasing, so I guess that's going to be a max. Let's change that. Local max for f, and x equals 5, that's the other switch, is a local min. So if we wanted to build sort of a preliminary sketch of what the antiderivative might look like, it might look something like this. Here's a 0, 1, 2, 3, 4, 5, and a 6. So here's a 2, that's a max, 5, that's a min. Maybe our function looks like it's increasing here, decreasing here, and increasing there. Maybe it looks something like that. But we kind of want to do better. This is a great sort of sketch, but the question is, can we add accuracy to our graph? That is, as the original question has asked, give the coordinates of the local max and min. We don't know whether this graph is all the way up at positive, maybe this is nowhere near the x-axis. Maybe this curve is occurring in a really positive or really negative way. We do have an initial condition, which is going to help us. Remember, this is a sketch of the graph f, but we really want to get the coordinates of the local max and mins. And the question is, how can we get information about the coordinates of an antiderivative if all we're given is information about the area under the curve of its derivative? And this is where the fundamental theorem of calculus comes in. So let's take the first region. This region has an area of 14. So that means the integral of f prime, because that's what this graph is, the integral of f prime from 0 to 2 is going to be equal to 14. So we're going to write that by the fundamental theorem of calculus, we know that 14 is equal to the area under the curve of f prime of x between 0 and 2. But the fundamental theorem of calculus tells me that this integral is going to be equal to its antiderivative, which is going to be just f, evaluated at 2, the upper limit of integration, minus its evaluation at the lower limit of integration, 0. But fortunately, we were given an initial condition that f of 0 is equal to 10, so this is now equal to f of 2 minus 10. And here we have an equality. F of 2 minus 10 on the right is equal to 14 on the left, so we can move the negative 10 to the left-hand side and we can solve for f of 2. So we'll say, so f of 2 now is equal to 10 plus 14, which is 24. Well, that certainly gives us information because 2 was a local max for the antiderivative, and we just found its coordinate. Apparently, 2 goes to 24. We can do that again for each of these regions. Recalling that the second region here is going to have an integral signed area of negative 20, we can again use the fundamental theorem of calculus. we'll say that similarly, negative 20 is equal to the integral from 2 to 5 of the derivative, which we know by the fundamental theorem of calculus is equal to the antiderivative at the upper bound 5 minus the antiderivative at the lower bound 2, which fortunately, by the previous line, we literally determined what f was at 2. So this is just going to be f of 5 minus 24, which if I move that 24 over to the right, I will end up with f of 5 being equal to just a 4. And if we do this for the third region, we'll end up with, remember that the proposed area for the third region was 12 from 5 to 6. Here we're going to get that 12 is equal to the definite integral from 5 to 6 of f prime of x dx, which by the fundamental theorem of calculus is equal to the antiderivative at 6 minus the antiderivative at 5, for which the antiderivative at 5 is a 4. So I'm getting f of 6 minus 4, so that tells me that f of 6 is equal to, once I move that 4 over, I get a positive 16. This information we have right here will allow us to build in a lot more accuracy for this graph we have here. And if we do instate some of that accuracy, we might end up with a graph that looks like this. Here's 1, 2, 3, 4, 5, and a 6. We know that by the initial condition, f of 0 is 10. We see also by the information we provided here on the right that the highest value seems to be a 24. So we're going to put these increments up to a 25, 20, 15, 10, 5. And so f of 0 is a 10, f of 2 is a 24, f of 5 is a 4, and f of 6 is a 16. And you could even write these in. This is 6, 16, this is 5, 4, this is 2, 24, this is 0, 10. And now when you draw the same sketch that we had up here, we have a lot more information to thread through our points. So we're going to have something that looks like this probably. And there it is. This is a much more accurate graph of our antiderivative little f. And so this helps to highlight the relationship that the fundamental theorem of calculus gives between antiderivative function values and the areas under the curve. And additionally, how we can utilize the information about increasing and decreasing to give ourselves initial sketches of what antiderivatives should look like. So really, it's very similar stuff to what we've done in the past. The only difference is, instead of moving in the direction of taking derivatives, we're sort of moving in the direction of undoing derivatives. The last thing I want to do is take a look at two more examples that sort of highlight these ideas once more. For example, here we have a slightly different function. Here we're told that a function's derivative is 2x plus 5. And we're given an initial condition that whatever the antiderivative is of f prime, we know that its evaluation at 0 needs to be at 3. And so the question is, what is f of 1? So for this question, the first thing we're going to ask ourselves is, what could f be? Well, we need to have some sort of a function that differentiates into an x squared and no x's. We know we can get an x squared by differentiating, say, a cube, and we know we can get no x's if we differentiate only one x. So let's see. We know that if I were to, say, differentiate x cubed plus 5x, I would get 3x squared plus 5. So the plus 5 seems to be matching up with what I want. The x squared is good, but I have a 3 here instead of a 2. So the question is, could I have picked a slightly different function to start with here that would somehow cancel out the 3 that came in and allow ourselves to replace it with a 2? And the answer to that is yes. We can introduce some sort of a constant. So let's try something like, let's differentiate maybe 2/3 x cubed plus 5x. In this case, we're going to get now 2/3 times 3x squared plus 5, which of course those 3's cancel, and I get my 2x squared plus 5, which is what I'm looking for. That's the same thing as proposed. So that means that this slightly augmented cube is going to be a good choice, but we have to remember that technically, I could have added any number at the end of this function. I could have added a 2, a 5, a 6, and etc., etc. So what that means is that f of x is going to be equal to 2/3 x cubed plus 5x plus magic c for some constant c. We have to determine what that c value is, but it's of course aided by the initial condition. So we'll say since f of 0 is equal to 3, this is equivalent to, well, we'll plug in 0, we'll get 2/3 0 cubed plus 5 times 0 plus c is equal to 3, and of course that tells me that c is equal to 3. So that means our very specific antiderivative is going to be 2/3 x cubed plus 5x plus 3. That's going to be the big antiderivative here. That's the big deal right there. Because once we have that antiderivative, we can now evaluate it at 1 and solve the day. So we'll say that therefore f of 1 is clearly going to be equal to whatever 2/3 plus 5 plus 3 is. It's some number, but that's going to be the answer. So again, this sort of walks through the logical reasoning that takes place in order to develop and guess kind of what an antiderivative should look like. Later on in this chapter, we're going to start developing more rules for determining antiderivatives, but this is a good way to start. The next question here says, here's a graph of a function f. We know f is the derivative of its antiderivative, capital F. We're given an initial condition on capital F, and we'd like to find the function value, capital F, at 4. Remember that if you want to find antiderivative values at a particular number, as we saw up here, the Fundamental Theorem of Calculus is very helpful in doing so, provided you can determine the areas under the curve of the derivative. Fortunately, this is a very, very easy looking function. If we highlight real quick, what we can determine is that this area is easily determined. We see that the area here is equal to, well, it's the area of this square, which is a base and a height of 1, plus the area of this triangle, which is a half of a square. So that's just going to be a half, which is 3 halves. We want to find f of 4. So that means what we're interested in is sort of cutting off our picture at 4, and then maybe we'll take an integral all the way up to 4. So we're also going to be interested in this area down here. But notice that this area down here is almost exactly the same area as up here. The only difference is it's negative. So what that means, so let's be clear here. So the area here is also equal to 3 halves, specifically unsigned. So what we're going to write here is that by the Fundamental Theorem of Calculus, we're wanting to investigate the signed area from 0 to 4 of this function f. And notice that it's going to be this area all the way up to 2 plus this area all the way up to 4. So here's one way we could organize this. We know on one hand, this, by the fundamental theorem of calculus, this is going to be equal to its antiderivative at the upper bound minus its antiderivative at the lower bound. But on the other hand, we could rewrite this as the integral from 0 to 2 of f of x dx plus the integral from 2 to 4 f of x dx, where you have to remember that this is giving me signed area, not unsigned. So here we're going to end up with a 3/2 for the first integral plus a negative 3/2 for the second integral, which actually are going to cancel, and I'll get a 0. So on one hand, this integral is equal to a 0 by looking at the area, but on the other hand, this integral is equal to, by the fundamental theorem of calculus, capital F of 4 minus capital F of 0. However, we also have the additional understanding that f of 0 is 0. So since f of 0 equals 0, what we find is that f of 4 minus f of 0 equals 0, if and only if literally f of 4 is equal to 0 as well. So that's going to be our final answer. This is an example much like the one we saw earlier in the lesson. The only difference is we had to actually compute the areas. It wasn't just given to us on a silver platter. So this is going to conclude our conversation in section 6.1. This is sort of an introduction into analyzing the antiderivative of utilizing graphs. Next lesson, we're going to jump into section 6.2, where we're going to continue to try to investigate this question of how do we find antiderivatives. But for now, take a crack at the homework on this that's related to this section. Let me know if you have any questions, and I'll catch you all in the next one.